Hi, welcome back to part 2 of this short Orbiter 2016 video series. The focus of this is just to illustrate some of the deficiencies of TransX when the thrust capabilities of the engines that you're using are low. And not in this part, but in the next part, we'll basically present a tool that can overcome some of those deficiencies and perform low thrust burns more accurately than the native TransX tool can in Orbiter. Okay, so in the last part we went through and just showed the basic usage of TransX for executing escape burns. For the example we had and used was we set up a trans-Venus injection from a low Earth orbit, 300 by 300 kilometer circular orbit. It was part of a Hohmann transfer that was set up using a PICAP program available from the European Space Agency free of charge. And we executed that, and we showed that the TransX works pretty well for the kinds of thrust capabilities of engines like the Delta Glider and also the XR2 and the XR5. What I'm going to do in this particular part is just reduce the effective thrust capability of the Delta Glider by a factor of 10 and rerun the same scenario. So if you haven't watched the first scenario, my suggestion would be to go back to the first part, watch that, and then come back and watch this one. We're going to basically pick up from the point where we got into orbit, or hot wire the scenario editor to get us into orbit, coplanar with the hyperbolic ejection orbit that we need to have in order to get into our Hohmann transfer orbit to Venus. So we are now currently 3,200 seconds away from the time to eject. The orbiter is paused, and I'll just set it running. And the first thing we're going to do now is, instead of working with the standard Delta Glider engines, we're going to use an MFD called rather ingloriously IEAT MFD to hotwire a reduction in the thrust capabilities of the standard Delta Glider. So if you don't have IEAT MFD installed on your machine, then I suggest that you go to Orbit Hangar and download it from there. Okay. I do have it installed on my machine, so I'm not going to do that. I'm just going to load it, and it's down here, IEATMFD. Click that, and it comes up with a bunch of numbers, and most of this I don't really need to worry about. The attitude hold I don't need to worry about. The reference body I don't need to worry about. The vessel, GL01, is being targeted, and that's the current focus vessel in orbiter, so that's okay. The main engine ISP is 40,000. I'm never quite sure what units is probably best for that, but I think meters per second is probably a useful number. It's effectively the exhaust speed of the exhaust gases from the engine. So in the standard Delta Glider, it is assumed that the exhaust velocity of the mass, the stuff coming out the back end of the engines, is 40 kilometers a second, and that's roughly an order of magnitude too high for even the most powerful chemical rockets that we have at the moment. That leads to a very high thrust of 320,000 newtons, given a flow rate of, I think, 8 kilograms of fuel per second. What I'm going to do is to reduce the thrust of the engines is just change that from 320,000 down to 32,000. So I've hit the engine button, little dialog comes up, and I'm going to put 32,000 in. And there you are. That's really all I need IEAT MFD to do. Just in passing, what does IEAT stand for? It's Ion Engine Attitude and Thrust MFD. So that's quite a mouthful, hence the abbreviation IEAT MFD. But it is an MFD used to help with navigation with low thrust engines. Okay, so that's really all I need that for. And I'm just going to get burn time MFD up. And I'm going to come look at some of the data here. The engine ISP is still 40 kilometers a second. Great. The engine thrust is no longer 320 kilonewtons, it's now 32 kilonewtons, 32,000 newtons. And the mass flow rate, it's achieved this by basically constraining the amount of fuel that can go into the engine. The default setting is 8 kilograms of stuff or fuel can go into the engines per second. But here it's now reduced by a factor of 10, so it's now 0.8 kilograms per second can flow into the engines, hence the tenfold reduction in thrust. Okay, so that's been set up. And now we're going to go through the same exercises that we did before in setting up the escape burn using TransX. And just let me open up TransX on this side, go back a screen, and then I want to go View, Turn Maneuver Mode on, variable over to prograde, put in the prograde amount, there we are, 3693 meters a second. Then variable over to, over to the date, adjust the setting to hyper, actually I'll go to ultra, and then swing it around until it overlaps the required hyperbolic escape orbit. Change the sensitivity setting, just work with this a little bit. And that's about as good as close as we're going to get using that technique. Alright, so now I need to begin the burn in 2008 seconds. So let me just get up, go to burn time calculator. I think it's probably easiest seeing it here. We'll get the burn from TransX and load it into burn time MFD by pressing the get button. Now, instead of a 156 second burn, because we have reduced the power of the engines by a factor of 10, we now need to run the engines for 1564 seconds. Roughly, what's that? About 20 minutes. So it's a 20-minute burn that we're envisaging, and we will need to start the burn in 2800 seconds from now. Okay, that's all good. What we want to do now is to go to the target screen, and we want to, just as we did before, we want to turn the auto center on, and the Delta glider will orient itself in the direction required by TransX in order to execute this burn. Okay, that's all great. Now we're still 2000 seconds away from the burn, so a little bit of 10x I think is required in order for us to get there a little bit faster, and even that's a little bit too slow, so we're going to go up to 100x and see how we get on with that. And around the planet we go. Whoops, a little bit of instability, let it settle down a bit, back up to 100x. Sometimes with high time warp, when the video recorder is on, it just has difficulty in running things forward efficiently at 100x, so every now and then you just have to bring it back down to 10x, let it stabilize, and pick up the time warp again. Okay, beginning the burn in 400 seconds. Get down a little bit closer. Right, we're now just about a minute away from executing the burn. What I want you to note, though, is that currently, well, even though we're 1 minute away from the burn, let's just go outside and just have a look at this. We are pointing towards the planet, towards Earth, to execute this burn. That's what TransX envisages. No, the standard usage of TransX requires us to have a burn that is at a fairly acute angle to the prograde orientation. We're actually 60 degrees off the prograde center. And in truth, I haven't actually done this burn before, so I'm going to be interested to see whether or not we plow into the atmosphere as a result of this, and just how accurate TransX will be when we go and execute this burn. Okay, we've got 19 seconds to go. I'm just going to let it, well, 35 seconds if you look at burn time MFD. Since it's auto-armed to do that, it's going to be 30 seconds to go, 6 seconds to go. We're now burning, and we are 53 degrees off the prograde orientation. We're at 310, 312 degrees, 308 degrees. So that's 50 plus 2 plus 3 degrees. And so we are now currently firing our engines as hard as we can, which is a tenth of what they normally are, straight towards, well, not quite straight towards, but at a 60-degree angle towards Earth. Doesn't sound optimal, and it isn't optimal. But that's what TransX wants us to do when we have some relatively low thrust engines. And if we reduce the thrust even further, then this discrepancy between our prograde orientation and the required direction by TransX becomes more acute. In fact, it just becomes complete nonsense. Anyway, we'll go with this for the time being. Now, it's a 20-minute burn. I'm not going to sit around for 20 minutes. So we're just going to go and hit 10x. And even that really isn't going to be fast enough. So I'm going to bring up the acceleration widget and just go up to 20 factor and 30 times. We should be okay with 30x. Now we're orienting prograde. Halfway through the burn, give or take. And now we're pointing away from the Earth. And basically the angle between our prograde orientation is steadily increasing, and it'll go up to about 50 degrees again. Again, not hugely optimal. And we're going to go down to 10x in just a few seconds. And we're going to go down to 1x shortly. And we're going to turn off the auto center. And then, yeah, we're basically done. Yeah, and this is the problem that we encounter with low thrust burns. Even though we set up the burn according to the standard TransX use, what TransX is telling us is that we completed the burn with, we were short 355 meters per second on the burn. So in order to finish off this burn, I now need to burn it for an additional 355 meters a second. And this is just for a tenfold reduction in the thrust capability of the engines. If you then have a further tenfold reduction to get down to a centi-G level of thrust, or another tenfold reduction down to a milli-G level of thrust, then these errors begin to grow exponentially, and it just becomes complete nonsense. Anyway, we'll just give you over to show this screen. This is the yellow line, if you remember, is the hyperbolic orbit that we need to be on in order to have our transfer, Hohmann transfer, as shown on the TransX screen on the right hand side. But we're nowhere near that. We need to burn for another, well, it says 445 meters a second here, so this is even showing a higher number. And so well, we'll have to, let's go to the prograde orientation for sake of argument. Okay, just a bit of 10x. And now we're going to set the engines going, try and eradicate that 400 meters per second. And we'll show you what happens when we do that. So I'm going to engines are going full bore here. We've got a little way to go, a bit of 10x to speed this thing up. And that's about as good as we're going to get. And we'll turn off the engines at this point. Maybe we'll just run them for a bit longer. And there you are. That's good enough for this demonstration. I would do this more tidily if I were inclined to do so and weren't making a video. But so we can match the delta V requirements, and it's close enough to 0 as to not make any odds for the purpose of this demonstration. But if you look down here at the semi-major difference, that's now up to 3.92. What is the semi-major difference again? This is, if you look at this yellow dotted line here, this shows the angle of, it points towards the periapsis of the yellow dotted line. So that's where we want to have, it's called basically it describes the argument of periapsis of our hyperbolic orbit. It shows the orientation of our orbit. This semi-major difference is an angular difference, so it says we're nearly 4 degrees out of true with respect to that line. So we are currently on an orbit that is was 4 degrees out of true. So if we had showed a similar green line coming down to our periapsis on our green orbit here, there would be an angular difference between the yellow dotted line and the green line for our current orbit of 4 degrees. And you can see that the manifestation, what impact that has. Basically, when we come a long way from Earth, we're no longer on a trajectory that overlaps with the yellow dotted line. And equally on the other side, the green line doesn't overlap the yellow dotted line. So we can match the thrust by just putting in a bunch more power into the engines, but we have a difficulty now that our final trajectory is no longer aligned with the trajectory that we need to have in order to get to Venus. And this presents a problem. We have to make a further correction in order to sort this out. And you're basically looking at hundreds of meters per second in order to sort this out. And the whole thing is quite unsatisfactory. Okay, so that describes where it is that TransX is beginning to fail. If we reduce the engine thrust capability of the engines down to something that is probably more representative of real spacecraft, TransX errors begin to grow rapidly as we reduce the thrust. Even at a tenfold reduction, bringing the power of the Delta Glider engines down to something that is probably comparable to state-of-the-art for current technology, we still have large errors. If we then go down to much weaker thrusts, which are probably which do represent engines that do exist, then we have an even greater problem. So the next part, basically we're going to show a tool that can be used in conjunction with TransX that overcomes this deficiency. And what it boils down to is if we get our timing right, then we can basically make sure that the green hyperbolic orbit that we end up on and the yellow hyperbolic target orbit that we want to be on do overlap to very high precision. But that'll be in the next part. Okay, that's that for now. Stay tuned for the next part.